All right, welcome to The Explainer. Our whole goal here is to take these big, complicated topics and just make them make sense. Okay, so to get our heads around one of the most important ideas in all of chemistry, we're going to start with something super simple, a question you definitely already know the answer to. See, in chemistry, a chemical equation is, well, it's just a recipe. Seriously, it tells you your ingredients, chemists call them reactants, and what you're going to make, which is the product. So far, so good, right? But hang on. Every good recipe has one critical thing this equation is missing, right? The quantities. It tells us what to mix, but not how much. I mean, are we talking about 1 atom of iron? A billion? How do we know? And this how much question, this is the problem. It's one of the most fundamental things chemists have to figure out like every single day. And believe me, getting the amounts right isn't just for passing a test. It has huge real-world consequences. We're talking about the exact dose in a life-saving medicine or the perfect mix for a super strong, lightweight material. If you get it wrong, well, at best, it just doesn't work. At worst, it could be a disaster. So to solve this massive problem, chemists came up with a really clever solution, a special counting unit. And honestly, it's kind of the hero of our story today. It's called the mole, and all it is when you boil it down is a name for a number, a way to count a specific and, frankly, enormous number of particles, like atoms or molecules. And when I say enormous, I mean just look at that number. That is Avogadro's number. It's just staggering. Here's a crazy thought. If you could count atoms at a blistering pace, say 10 million every single second, it would still take you over 2 billion years just to count 1 mole. It's that big. You know what? The best way to think about this is super simple. A mole is just a chemist's dozen. That's it. You know a dozen means 12 of something, right? Well, a mole just means that ridiculously huge number of something. It's just a word for a giant quantity. Okay, but here's the obvious problem. You can't count atoms, right? They're way too small. So how on earth does this giant number help us actually weigh something out in a lab? Well, this is where the genius of it all really kicks in. The answer is a beautiful little concept called molar mass. I want you to think of it like a bridge. It connects the invisible, impossibly tiny world of atoms to our world, the world where we can use a scale and measure things in grams. Molar mass is literally just the weight, in grams, of 1 mole of anything. And here's the crucial part. This number isn't just made up. It's a fundamental property of every single element. And the best part? You don't have to memorize it. It's right there for you on the periodic table. See that number right below the element symbol? Boom, that's its molar mass. So to keep track of how all this fits together, the mass in grams, the number of moles, and the molar mass, chemists use this super handy little triangle. It's like the master key for doing the conversions. You just cover up the thing you want to find, and the triangle literally shows you the formula. Pretty cool, huh? All right, let's actually try this out. Let's say we have a chunk of iron that weighs 111.7 grams. How many moles is that? Okay, step 1, we look at the periodic table and find the molar mass for iron. It's 55.8 grams per mole. Step 2, we use our little triangle. We want moles, so we cover that up, and it tells us to do mass divided by molar mass. So, step 3, we plug in the numbers. 111.7 grams divided by 55.8 grams per mole, and what do you know? It comes out to exactly 2 moles of iron. See? It works! Okay, so now we have our magic tool. We can translate a weight in grams into a specific count of atoms using moles. So let's go all the way back to our chemical recipes and finally solve that how much problem. By the way, this whole area of chemistry has a fancy name, stoichiometry. So let's look at a real chemical equation, like this one for making ammonia. Before, those big numbers in front might have seemed kind of random, but now they have a powerful new meaning. They aren't just numbers, they're the mole ratio. This is the actual recipe. And just like that, boom, we've solved it. We've solved the how much problem. This isn't a suggestion, it's a non-negotiable chemical law. It tells us that exactly 1 mole of nitrogen must react with exactly 3 moles of hydrogen to produce exactly 2 moles of ammonia. No guesswork, no maybe, just pure, precise chemistry. So, okay, that's cool for a chemistry class, but why does any of this really matter out there in the real world? Why is this one concept so important? Because the mole is without a doubt the central hub for all of chemistry. Think of it like a capital city where all the roads meet. It's the universal translator. As you can see here, it's what lets a chemist connect the mass of something to its concentration in a liquid or its volume as a gas. Everything flows through the mole.
Mastering the mole is what gives us the key. It's what unlocks our ability to actually control and manipulate matter on an atomic scale, to literally build the world around us. It's how we can precisely control reactions, calculate exactly how much stuff we're going to make, and manufacture, well, everything. From the fertilizer that grows our food to the life-saving drugs in our medicine cabinets, we are literally building our modern world one mole at a time.
So, you see, the mole isn't just a number. It's the tool that allowed us to build the molecules and materials of today. Which leaves us with one final, exciting thought. What are we going to build with it tomorrow?